So we can't do 2 hours associated class, so we'll do 2 consecutive classes.
What is the test total? What material is covered?
Everything we've covered up to this point.
Oh, everything up to this point. So holes under rotation and that stuff all is on.
All the stuff we're even talking about now.
So the last one assignment?
Let's see here.
Or this coming one assignment. Yeah, like this, well, the last one I want that.
So the assignment, the homework assignment on which you're working now
Okay.
will be a part of. All right. So now we're going to talk about bending. Essentially, looking back over what we've done, we've looked at the implications. So let us reflect, since we're not going to have a review. So we've gained an understanding of stress and strain. This idea that we don't measure, in real materials, we don't care so much about the force or the force, we worry about the stress, and force per unit area. That's the characteristic that matters in terms of characterizing materials behavior. And then the response to that stress is a strain and elongation. And then there's also shear stress and shear strain. Shear strain is a shear, is a change in shape. So we started off just talking about tensile loads, right? Just pulling along the length of a shaft. And then we next talked about torsional loads, twisting the shaft and creating shear stress at the surface. Now, today, we're going to start talking about bending loads. So we're going to take this shaft, the end of the shaft that's pictured here in figure 618, and bending it upward, rotating it upward. Okay, so creating a moment about the z-axis. Does that make sense? So in this case, there will be no normal component of stress. There will be no shear component of stress. It is just a bending moment. There's no torsion, just a bending moment. And then in the end, we can superimpose everything. We use superposition to add together a multi-dimensional stress state. But we've analyzed each of the other rotations. Now we're going to analyze bending. Okay, and bending, so essentially we're rotating a moment. Torsion is a moment about the x-axis, as pictured here. Bending is a moment about the y or z-axis, right? Because y and z in this configuration are interchangeable in this sort of generic bending situation. Just like we had forces that are in the x-axis are normal forces, and any forces in the y or z-axis are shear. And we don't differentiate between shear in the y and shear in the z, because that's some random decision of how we want to orient ourselves. Does it kind of make sense? That make sense? So this is the last loading configuration, the last unique loading configuration we can have. We've done we have done forces in the x, y, and z. We've done moments in the x, and now we're doing moments in the y, z, and we're done. Okay. Then we'll start. Well, we're not done. We've got a whole semester left, but anyway. Okay. So we call these moments oriented along the y or z direction bending moments. So if I take a slice out of this thing, so here's the second figure. There's sort of the macro view, right, of this thing being bent, and I'm going to take a slice out of the center of it. You can see the slice delineated there, the delta x slice. If I take the delta x slice, while it's being bent, that slice becomes a trapezoid. Actually, let me draw that trapezoid a little lower on the screen, on the board. And I'm exaggerating the angle of the trapezoid for the purposes of demonstration. Okay, so there's some center of rotation for that particular slice. Okay, everybody kind of see that? Some origin about which Those two sides have been stretched. Just giggling over here, what's going on?
Nothing.
Your hair's just happy to be out of the hat.
It's really happy, actually.
Okay. All right, so there's some middle plane here in which the width, delta x, is the same as it was before it was deformed. Right, so there's some plane. If I bend this thing around, I stretch the outside, I compress the inside, but there's some plane in the middle where there's no stretch of any kind. No stretch, no tension or compression. And so that's the neutral axis. That would be the neutral axis, the plane that does not experience any tension or compression. But there's some dimension down here, labeled in the picture as delta S prime, I think, which is smaller than delta x. Right? So we want to figure out, well, delta S prime, the dimensions of delta S prime. So we have this distance here, the radius of curvature, if you will, back to that origin point. From the neutral axis back to the center of the curvature. And there's some point, delta S, that is a distance y away from that neutral axis. So delta S is rho minus y divided by rho times delta x. Rho minus y is this piece. So we're essentially taking two similar triangles here and comparing them in order to get delta S prime.
Did you say delta x was the undeformed?
Delta x is the undeformed. And you can see it in the picture on the left-hand side of the picture here. Before you've undeformed, everything's delta x. Everything in the slice is delta x. So delta S prime is that. Does that make sense? It's just some more triangles. And delta x, in this picture, I'm going to use theta, is equal to rho times delta theta. Again, you can see that on the picture as well. So if I combine those two together, I get delta S prime is just equal to rho minus y times delta theta. Right? Rho minus y, this piece, times delta theta gives me delta S prime. Everybody? So let's say I want to find the strain at that plane, delta S prime. What would the strain be? How would I calculate the strain?
Is that the change in distance over area? Change in distance from x, delta x, delta S prime.
Okay. So you're saying delta x minus delta S prime over something. What did you say it was over?
It's like area times something.
Area times something? Anybody want to help him out? Definition of strain?
Must be over delta x.
It'd just be over delta x.
Uh,
Because it's the change in length divided by the initial length.
So, at some points, does it have like negative strain? Because
Right,
it's
right, so
below
this,
it?
right, because this is negative, this, at some points it's negative, and some points it's positive.
Okay.
And it's actually, I won't push you guys to correct this, actually delta S prime minus x, it's final minus initial. But, move it up. We got it there eventually. Okay, so does that make sense? So that's essentially delta S prime over delta x minus 1. Well, that's delta S prime over delta x from up here, that's equal to rho minus y over rho minus 1, which is equal to, if you do the math, minus y over rho. So as y increases, strain decreases. Right, becomes more negative, it's compression. In other words, when we have positive values of y, we have negative values of strain, it's in compression. According to our convention, remember the convention? For force, strain, all that kind of stuff, compression is negative. That's why the minus sign ends up in there. Right? Okay, if that's the strain, then what's the maximum strain this little slice sees?
Would it be from delta x, like the y distance from delta x to the side of the y distance?
Okay, what would be the distance from delta x to the y? So what have we been using, for instance? Okay. Let's say it's a round bar. What would that be? It would be the radius. Okay, if it were a round bar. So the way we've been doing that would be minus c over rho. And c was the radius of the.
Is it connect, is the, what do you call it? The neutral axis straight through the middle necessarily?
Not necessarily. We'll define where this neutral axis is in just a second.
But in a round bar it is?
But in a round bar, it is right through the center, yes.
Okay.
Okay, so far everything makes sense based on, again, we're deriving this based on stuff we already know, so it shouldn't be, it should just be applying what we know to a new situation. All right, well, we also know that as long as this is elastically bent, as long as we're not plastically deforming it, and we're bending it in a way that it can bend back, which is generally what we want to do with everything, right? You don't want to plastically deform the beams of the building you're working in, right? So you want to, as long as it's elastic, then we know that sigma is proportional to epsilon. The stress is proportional to the strain in an elastic regime, right? So sigma then must also equal minus y over rho, and sigma max must equal negative c over rho.
C.
C is the radius of the round bar, if this were a round bar.
Wait, so why isn't there the, what's it called? The capital E constant? Isn't that how you write it?
Yeah, you're right. I mean, technically, yes, you're right.
Okay.
Let's leave those, because I'm going to get rid of the proportionality in a second.
Okay.
So sigma then, solving for rho and plugging in, is equal to minus y over c times sigma max. So sigma max would actually be equal to minus e times c over rho. Because sigma and epsilon are true. Okay, so a couple things to note. If you think about it, think about each element in this little wedge. Every element in this system experiences only normal forces. There are no shear forces in this system. Every little block, if you went through and looked at every little cube of material, it is only being squeezed in this direction. It's only experiencing a normal stress. There are no shear stresses in a bending configuration. At least to a friction approximation, until we get to, if we get to really severe bending, okay, it'll be a little bit different. But as long as we're working in a linear elastic regime, there are no shear stresses. Everything is a normal stress. Okay, so this is all we need to worry about. We don't have to worry about tau. There's no taus generated in this configuration. Okay. All right. Okay. All right. So now let's zoom in on just one face. Let's see. Do I have a picture of this? I don't know if I've got a picture of this. No, I don't. Okay, let's zoom in on one face of this bent bar. Okay, because I mean, it's wherever on the bar. We have this neutral axis here. And that's the neutral axis. Where when the bent bar is bent, right, the moment applied is this one. When the bar is bent, with this positive moment, the neutral axis is not deformed. Everything above it is squished, everything below it is stretched. Okay. Now let's take a little segment here and look at the force that's acting on that segment. There's going to be an internal force acting there caused by this internal moment, M. Right? So dF, the element of increment of force, is equal to sigma dA, where sigma is the local stress at that location. Okay? There's a stress at this point, creates an increment of force, which is that stress times the area dA of that little square. Force times stress times area equals force.
Sorry, I've got a question I kind of got. So a moment on like a rod is created from a force that is perpendicular to the rod, correct?
Right, so a moment, or it could be an implied, you can imply a bending moment that is not the result of the force.
Okay.
Right, I can twist it from the side.
Oh, like this?
Right, so I go like this with a screwdriver on the side, you know, if I stick a screwdriver in a slot and go, right, so locally, there's gonna be some force, yeah, there's a force pushing down here and a force pushing up there, and you know what I'm saying, if you zoom in. But the macroscopic view on the bar is just a moment.
Okay.
There's no net force pushing upward. When I stick a screwdriver in a slot and twist it, I'm pushing down just as hard as I'm pushing up. I'm not actually applying any net force. But it's a force couple, right? Two forces equal in opposite directions, separated by a distance. So there's a force couple, which is an applied moment. Does that kind of make sense?
Yeah, I guess the thing I was saying is because we said there's no shear stress in the beam.
Right.
But I guess I was thinking if there's a force applied
Then there
perpendicular,
could be, right,
and you would think that there would.
Right, so this is not the moment resulting from a force, a bending moment resulting from an applied force. This is from a shear. This is an applied moment. So we've looked at what happens when you apply forces already. Now, and we've looked at what happens when you apply torsions already. Now we're looking at what happens when you apply a bending moment. Then we'll have covered all the bases for all the things you could have applied. And then an individual beam that experiences multiples of these things, we can analyze superpositionally. That's a word. That kind of makes sense.
Yeah, I got you.
Okay.
So,
Last question. So,
Somehow I don't think that's probably true.
well, maybe just today. So if I took a piece of bar like this, bent in my hands, is that a local moment, or am I applying force at either end and then causing a moment that way?
So when you bend a bar like that, right, your hands are each applying a couple. You're applying an upward force and a downward force that are equal and opposite, but separated by a distance.
Right.
Those are applying bending moments.
Okay.
Okay. So, but the thing is, realistically, on a macro structure like this, if you did it, you know, if I was bending a piece like this, I'd probably handle it in terms of forces rather than in terms of moments, because the macroscopic distance of my couple, you know, the separation of my couple, is comparable to the dimension of my system. Right? That's why I used a screwdriver as an example. If I got a bar like this and I apply a screwdriver like this, I'm going to apply a bending moment to the whole thing, but the couple distance is very small compared to the overall dimension of the bar. So it's effectively a point application, a concentrated application of a bending moment.
Okay.
Okay. Everybody good? Okay. So, element of force acting on that bit, sigma dA. But I really care not just about that force, I want to know what is the total force acting on that end face. So the total force is the integral of sigma dA, right, from the bottom to the top, right, over the entire area of that end of the bar. Okay, well, we have sigma, we have an expression for sigma, right here. Plug that in, means that's the integral of minus y over c times sigma max dA. Sigma max is constant for all points on the surface. It comes out. C is constant for all points on the surface, so it comes out. So the total force is just minus sigma max over c times the integral of y dA. That's the total force acting on the end face. What is the total force acting on the end face? Give me a number. Be more definitive. 0. Not 0. 0. Come on, try.
0.
Yeah, exactly, it's 0. That's what I started out with. I said we were doing a bending thing, right? N, well, that's not an N. N equals V equals 0. There are no normal or shear forces. So if I take any slice, there is no internal, normal, or shear force. Right? We have this big long bar that we started out with. All I'm doing is bending it. There's no normal forces acting on the bar. So there's no internal normal. If I did a section at any point, there would be no internal force on this face. So this integral, or this force, has to equal 0. Is sigma max can equal 0? Yes or no?
No.
No, thank you. At least somebody's paying attention, trying to participate, trying to engage with their education. But you know, the rest of the other time. Is C going to be infinite?
No.
No. Well then sigma max over C is not going to get me 0. This thing on the other side is going to get me 0. What is that thing on the other side? What is the integral of, the area integral of y dA?
The volume?
No, it's not the volume. Y and A are both in the same direction. It's not dA. Anybody recognize this from perhaps, oh, I don't know.
Oh, the moment.
No, it's not the moment. It's not the moment of inertia.
It's
Something.
Centroid.
It's the centroid.
something.
Right.
from
When this is equal to 0, when that integral is equal to 0, then we have defined our centroid. Right? This integral is only equal to 0 when it is taken with respect to the centroid. Therefore, the neutral axis passes through the centroid of that face. Okay? Now everything we're talking about in this section assumes that we have symmetry in the direction into the board, in the z direction here. Okay? So we actually pass through the centroid in both directions, because since it's symmetrical, the axis goes through this, you know, the physical center of the z direction and then the centroid of the y direction. So if this is a triangle, like you'll see we have in our first problem up there, right? Then we have to define the neutral axis as being the centroid of this plane, but the centroid in terms of the z direction is just the center because it's a symmetrical beam. Friday we'll talk about unsymmetrical beams, which seems like a weird word, but it is.
So,
Yes?
do we still call it C if it's a triangle?
It's still the centroid.
No, the.
Oh, the dimension C? Yeah, no. No. Well, I mean, we still call it C, but it's not the radius.
It's not the
C is the maximum dimension.
C, is it?
Okay? But that's okay, just hang with me for a little bit. Okay? All right. So, because we know that the force is 0, we know that our neutral axis must pass through the centroid. But we do have an internal moment, M, right? Which is the applied moment for the simple case of the bar with a single moment. Right? So we also know that M, that applied moment, is equal to or I'm sorry, dm, the increment of the element of moment created by this force that I've drawn here in this little increment, is going to be y times df. Right? df is the increment of force for that little area. Y is the distance it is away from the center. Y times df gives us our moment. So that's equal to y sigma dA, same thing we did over here. And then if I integrate, I get that the moment applied is equal to the integral of y sigma dA, which is equal to the integral of y times negative y over c times sigma max dA. Sigma max and c come out. Negative sigma max over c times the integral of y squared dA. That is my moment. Now, does anybody recognize, now is that moment going to be 0? Why not, Clayton?
Because there's an external moment being done.
That's a lovely job you've done of throwing your voice there, Clayton.
Thank
Very
you.
impressive. You took it up an octave and everything. It was great. So, yes, no, the m is not going to be 0 because there's an applied moment. That's the thing that's being applied to this bar. So whatever that applied moment is this times that. What is that? It's the moment of inertia. Right? The integral of y squared dA is the moment of inertia. So the moment that's applied is equal to minus sigma max over c times the moment of inertia I. I can rearrange that and solve for sigma max. Sigma max, therefore, is equal to mc over I. Because this is what we're after, right? Again, we want to know the stress state in the bar. That's where we started. So we're trying to find the stress state. Well, the maximum stress state is mc over I, or the stress state at any other point within this volume of material, or within that interface, is going to be my over I. Actually, I forgot I left out my minus signs. So what does that tell me? That tells me that my stress as I leave the neutral axis, as I move away from the center, my stress increases with distance linearly and depends on the ratio of the applied moment to the moment of inertia. And it's negative. As I go up in y for a positive bend, I get a negative stress, therefore compression at the top and tension at the bottom. And again, the reason that that's true for a positive m, the reason this is a positive m is because it's causing it to cup concave up, right, to hold water. So this positive m gives us a negative compression on top. Okay, so this end equation, if you will, that we care about is this one. Okay, but I want to make sure you understand how we got there. I don't want to just sort of, here's an equation, go use it, you know. We've got to have some kind of appreciation of where it comes from. Okay, but that's why we went through the moment of inertia discussion last time. Because if I have some randomly shaped bar that's not a nice circle, or even if it is a circle, I've got to know the moment of inertia of that system. Okay? So for instance, any questions? Okay? So for instance, let's say I have a triangle. I'm going to have to know, if I want to find out about the stress in this triangle, to which I'm applying a moment, I'm going to have to know its moment of inertia. Okay? All right, remember, as the triangular cross-section shown, determine the largest internal moment that can be applied to the cross-section without exceeding the allowable tensile and compressive stresses of 22 and 15 KSI respectively. Okay, so the maximum in tension is 22 KSI, and sigma max in compression is 15 KSI. And we want to find out how much of a moment this triangular beam can support. So where shall we start?
I don't know, I set a free body diagram.
Start free body diagram of what?
Yeah.
Would you like me to offer a suggestion?
Yeah.
Let's do a free body diagram of the end face. Okay, so we're just going to take this beam and draw its cross-sectional end face. Okay, and we know that it's an equilateral triangle, so this is 2 inches. 2 inches over here, this side is 4 inches, right? The height is 2 times the square root of 3 inches. Is that in there? Man, it's not important. And then we have a neutral axis. Do we know where the neutral axis is?
I'm gonna say 1/3 from the bottom.
I mean, it's 1/3 from the bottom.
That's center.
All right, so this distance here is 2 square root of 3 divided by 3. The height, total height is 2 root 3. So that distance is 2 root 3 over 3. And that's our neutral axis. Okay. Now what?
Analyze at the very top, at the very peak, and then analyze at the very bottom.
At the very peak, okay? And at the very bottom, you said. So we want to analyze those 2 points. Okay, which one of those is in compression?
Top to peak.
The peak is in compression. So we have compression up here, and tension down here. Right, because of the way that the moment has been applied. So we want to evaluate the top to see if it fails in compression, and the bottom to see if it fails in tension. But we don't know what the applied moment is. They're asking us, what is the largest internal moment that can be applied? So what do?
Well, we know our max, and we can solve for our moment of inertia. So we just set our
So
equation.
moment of inertia equals what? I'm sorry, not moment of inertia, not n. Moment of inertia equals what?
Square root of y squared dA, square root integral.
Integral of y squared dA. Okay, so we can do this every time we get a shape. But it's generally a lot easier if we have regular shapes to open the front cover of our book. And in the front cover of our book, we will see a list of well, our book anyway, maybe not the international version. For those of us who have the US version, the legal version of the book, there is inside the front cover a geometric properties of area elements table. I'll take this moment to share with you that what you will have on the exam as a reference will be what's inside the front cover and what's inside the back cover. I will give you these 2 pages and these 2 pages on your exam. Okay, and I'm typing them up now. I scanned in the version from the online, but it's not good, so I'm manually typing them out now. And hopefully we'll have that for you by Friday, so you can actually have a copy while you're studying over the weekend. Okay.
So all the equations needed to do problems, we need to memorize?
If you need anything that's not on this, you need to memorize it.
Okay.
Okay? So this is what, and this, I'm giving you the whole thing at the beginning. So there's things in here you're like, we haven't even talked about that. Right? There's stuff here we haven't talked about yet. But I'm giving you the whole thing for all 3 exams. Okay. But we notice that for a triangle, I of a triangle is 1/36 BH cubed. Does anybody else have an actual copy of the book?
No.
So that's probably going to be the easier way to go. And base is equal to 4, and the height, as I said, is equal to 2 times the square root of 3. Okay? So we have our moment of inertia. What else? What now? Well, you into what equation? You don't have an equation yet. I'm not really going to use that equation. I'm going to rearrange that equation first. All right, that's probably the better way to go. All right. Do I know sigma max? All right, so I know it for each of the 2 conditions. It's different for the 2 conditions. Do I know I? I've got I. Do I know C?
You want to go and read
Oh, it's already
the,
written.
C is just the distance.
Well, one of them's written, yeah. C is this distance. This is the C for tension.
So we put up and it's right there. If we really wanted to, we could look it up.
This piece, I didn't draw that very well, is 4 root 3 over 3, and that is C for the compression side. Okay? All right, so let's see, get some numbers here. Which one you do first, compression or tension? Okay, for the compression, we've got 15 times 10 to the third times, what's I? Oh, actually here. They calculated I. 4.6188 inches to the 4. That's I for the sample. Plugging in these values. So that's 4.6188. And actually, you know, because we're working in English units, I'm going to go ahead and put the units in there. Let's see. Yeah, they didn't do that. It's going to be, hold on a second. 2.3094, I think. Anybody got that? No. So much for I got your back, guys. I'll just make up numbers then, nobody seems to care. All right, and we do that, and we get M for compression is 30 times 10 to the third kip inches. Which if you divide by 12 is 2.5. I'm sorry, not times 10 to the third. 30 kip inches, which is 22.5 kip feet. Okay? So I guess I could drop this and left it in K, kips,
Wait, what is giving
1,000 pounds. Okay, so really, if I want to come up in kips, somebody else is using numbers, this just becomes 15 kips per inch squared. And then everything's in kips and inches. Okay? What do I do now? Do I have an answer? Is 2.5 kip inches the maximum moment that can be applied without exceeding the allowable stresses?
You don't know until you do the other.
Yeah, I don't know until I've done the other side too. I've got to do the tensile side as well. So the tensile side, again, same approach, but now it's 22 kips per inch squared times the same moment of inertia, 4.6188 inches to the fourth, divided by what is C for the tensile side? 1.1547. Half of the other one. And in that case, I get 88 kip inches, which is 7.33 kip feet of moment. So, how's it going to fail? It's going to fail in compression. Because to reach failure, I need only 2.5 kip feet in compression as opposed to needing 7.33 kip feet in tension. So the answer to the question would be what? 2.5 kip feet. Okay? What if I bent it the other direction? Right, this was it bending upward. And we have the same limit bending it downward?
You have to switch your maximum.
Your stress max.
So, what is M compression going to be equal then?
15 times the, yeah, other than 1.1.
And the M in tension is going to be 22 times the 4.6188, but now divided by 2.3094. And I would ask you guys to figure out which is which, but we don't seem to be interested in actually doing any calculations, so not sure what we can do there.
Would you like us to calculate them?
I would like to. I mean, I thought perhaps, you know, we'd be in here trying to figure this out just to make sure we got the right numbers.
We just trust you.
You're the captain
Foolish
of our.
foolish on your part.
Is that duct tape?
No, that is a leather tie.
It's actually really
It's
awesome.
actually leather.
Is that
Here's Keith.
That looks really uncomfortable.
I think it was sweet.
Why would it look uncomfortable?
Oh,
Top one's 60.
Top one is 60.
well, 5.
Bottom one's 44.
44
Jesse won.
kip inches. What is that in kip feet?
3.67, well, the top one's 5 kip feet, the bottom one's 3.67.
So it says then what? If I bend it the other way?
Tension breaks first.
Tension breaks first. But which way is it stronger?
Second.
Bending it down or bending it up?
Getting it down.
Bending it down is stronger. It takes 3.67 kip feet to get it to fail bending it down. It only takes 2.5 kip feet to get it to fail bending it down. Okay? So, but that's probably why you typically don't see asymmetrical beam shapes. I mean, it's not, that would be an uncommon kind of configuration. But if you did, and we've also assumed here that the failure in tension and the failure in compression are different. In many materials, they're the same in both directions. All right, before you get all antsy about jumping out of here, I'm going to at least tackle the beginnings of the next one. Unless Colin asks me a delaying question.
Sorry. Okay, so
Hey,
bending.
wait, he said that was his last question for the day
Did say
earlier.
that was-
Go ahead.
Okay, but if I ask Blake, can Blake ask you?
No, that's fine, go.
Okay, and so when you bend it down with the corner
Pointing out.
pointing up, that's stronger when that's weaker than bending it up?
Which one's stronger? Bending it down or bending it up? Bending it down is stronger. It takes 3.67 kip feet of moment to get it to fail. Bending it downward, it's 2.5, a much smaller moment to get it to fail bending it upward.
Okay.
Okay. All right, look at the second problem. Determine the moment M that must be applied to the beam in order to create a maximum stress of 80 megapascals. Also sketch the stress distribution acting over the cross section. I'm not so much worried about the sketches. The sketches require some artistic skill. Basically, if you look in the book, I haven't drawn anything up here, but if you look in the book, there are pictures of, sort of three-dimensional pictures of a sloped surface, where here the stress is going in, and here the stress is going out, and it's linearly related to y, so that they're flat surfaces coming out. And don't worry about that. But determine the moment that must be applied to the beam in order to create a maximum stress of 80 megapascal. So, what are they asking in the second question, 676? Right, so how are we going to approach it? Same way, right? We're going to do the same thing. We're asking for the...
Oh.
All right, somebody scare her. They're going to do the same thing. What's the complicated part for this one?
We just set it up a little bit differently.
Feel free to smack me. What's the more difficult part for the second one? Go ahead, Blake, what were you saying?
Multiple unit surfaces.
Yeah, we got all kinds of different pieces, right? So we got to find a moment of inertia of this complex structure. Finding I is the tricky part for the second problem. And I will offer you the same suggestion as I did before, and that is that the I for this whole piece is going to be I of the overall box minus I of the open spaces. So your first I, the I of the box, is 300 millimeters wide, 300 millimeters high. It's a square, right? So the moment of inertia for a square, you get, well, actually they don't even have square, they just have rectangle in here. But it's 1/2, or 1/12 the side to the 4th power for a square, okay? The open areas are rectangles. There's 2 of them, so you could do it as 2 of them, or you could recognize that if I have a rectangle here and a rectangle here, and I'm talking about the moment of inertia, about the neutral axis here, that's the same as if I had one big rectangle that's the width of the 2 small pieces. So essentially I'm going to subtract a rectangle that is 260 millimeters high and 210 millimeters wide. Again, 1/12 ph cubed. okay? And then once I've got the moment of inertia, the rest of the problem is pretty straightforward. Any questions?
So, would you just do like a stress times y, because your y still be the same, times the addition of all your inertias, or if you're to do
Right,
separate?
you have a component, or a compound and moment of inertia. Calculate what that moment of inertia is, and then you come back here.
And because your strain is the same in all.
Yes,
Will you be around me?
The strain is going to be the same.
I can explain it to you.
Strain will
Right here.
depend only on distance from the neutral axis.
For what?
So if it's this piece or this piece or this piece, if I'm, 10 millimeters from the neutral axis, they all have the same stress. And if I'm at the very top, they're all the same distance from the neutral axis, they'll have the same stress. Actually, I guess they don't really want to erase the video.
It's not.